Now we move to the next speaker. Is Dr. Chen Liu. He's a professor with the Department of Mechanical Engineering at the National Chen University. His research interests include mobile robot network, bilateral teleportation systems, and human-human interaction.
It's better?
So whenever you're ready, you can start your talk.
Okay. Slide. It's not in full screen. Okay. Okay. Thank you very much for the introduction by Professor Funada. I'm Chen Liu from National Chen University in Taiwan. So it's my great pleasure here to share our latest research in human-robot interaction. So the title of my talk today is Human in the Loop Coordination Control for Multi-Robot System with Task Abstraction. So in my university, I'm also the director of Naval Robotic System Lab. So we have been working on multi-agent systems, including the consensus and synchronization. So which we focusing on how to design the communication topology or the control law or to deal with unreliable communication so that a group of mobile robots, they can achieve a certain agreement, including synchronization or consensus. And then we have been working on like event trigger problem or switching topology, or even now focusing on resilient control, which means that when there are cyber attack, including reception attack or replay attack in the communication, then under all this attack, how can we have the multi-agent to achieve consensus and synchronization? So in addition to that, we have also been working on the wireless sensor network coordination with the mobile robot network. So in this research, we assume that there are a lot of wireless sensors distributed in the environment. And then those sensors can acquire sensory information at that location. And those data are transmitted to the mobile robots. So the mobile robot will use those sensory data to estimate what is the density function of the environment. In the meantime, they will use that density function to accomplish coverage control of the system, of the environment. Yeah, and then recently we are working on the multi-agent cooperative transportation system. So AGV has been utilized widely in industry to transport objects, to transport materials, and then but for different size of different weights, we need to design a specific AGV for that. So the main idea is that we want to design a modularized AGV, and then if we want to transport a large cargo or we want to transport a very heavy object, then we can use multi-AGV to do that. So just like the video you see on the right button, we can control 3 AGVs to keep a formation, to change the orientation and moving in the environment. But among this research, we focus on multi-agent system, but there's no human inside. So even so, the agents, they can autonomously achieve a predefined task. But if there are some change in the environment, or if there are some other suddenly impact, or we want to change the task, the robot, they cannot do that. Okay, so we consider that that's maybe a kind of a limitation to this kind of research. So we want to see whether it's possible to add a human inside the loop, so that the human can interact with those mobile robots to deal with some unexpected situation. So this is recall to our very beginning, very early research. That's the bilateral teleoperation system. In bilateral teleoperation system, basically we have 2 robotic arms on 2 sides. One is in the local side, another one is in the remote side. So the robot in the local side is manipulated by a human operator, and then the information, for example, like the position and velocity, are transmitted over a network to a remote robot in the remote side. And the robot in the remote side will, like motion copy, will do the same thing. And then the states will also feeding back to the master robot. So the human manipulating the master robot will feel something like force feedback, or to see what's going on about the slave robot. So traditionally, bilateral teleoperation system was developed in the joint space, which means that the degree of freedom for the local robot and the remote robot should be the same. But in this operation, actually the human is holding the end effector, and then the remote robot is using the end effector to grasp some tool to do some manufacturing missions. Okay, so we are thinking whether it's possible to design a controller so that the teleoperation system can be accomplished in the text space. So in this research, we have done that, and then if there are communication delay, the slave robot, or we call that remote robot, can still follow the human's command. In addition to, because we focus on text-based control, so the number of degree of freedom for the local robot and the remote robot can be different. Okay, so like what you see in the upper right simulation. So the slave robot can follow the trajectory from the master robot. In addition to that, it can change its configuration in the null space, in the redundancy, to avoid obstacle showing in these two circles. So we are thinking, okay, this is good because if we want to control a robot, for example, like a mobile robot, the degree of freedom must be different. Okay, so after that, we find out that there are two papers published in 2003 and 2006 by Dr. Bishop and Dr. Antolini. They're considering how to control a pattern of autonomous vehicle based on the redundant manipulator technique. So this is just like what we made for the slave robot. So we are going to combine these two and then to design a so-called semi-autonomous teleoperation system. So in this system, the human operator only need to manipulate the local robot, and then it will be the text function, the text base will be utilized to control the swarm robot. Okay, but for the controlling the swarm robot, it's not one-to-one. So we need to see what is the function that we can design for the swarm robot so that the human can interact with. So initially, we consider, sorry, there should be, okay. So initially, we, based on this framework to design the task. So for the swarm part, there should be two sides. The one is for the main task that is directly operated by the human operator. Another one is because the swarm itself is a redundant system, because the number of degree of freedom is higher than the text-based dimension, so that we can control the group of swarm in the null space, so that this leads us to the design of the secondary task. Okay, so here is our objective. We want to propose a system framework and control algorithm that can enable a human operator to simultaneously, in real time, interact with a group of swarm robot in the remote environment. And then in addition to control the main task, we will also want to use the redundancy to make sure that the swarm robot have the ability to autonomously interact with the environment. So the human only need to care about what is the main task and whether the swarm robot satisfies the main task. And the secondary task is accomplished in the null space, and then the human operator doesn't need to know that. So initially, for the main task, basically we focus on two things. One is the average precision, because if we have a swarm, we want to control whether it's a swarm going to a different position. Another one is the position variance, because we also want to see how large is the distribution of the swarm robot. So based on these two main tasks, we design a control algorithm. So these are the dynamic model and for the local side and the remote side. The main thing we want to mention here is for the text-based function. For the local side, the text-based is based on the manipulator using by the human operator. So it's just like a forward kinematics, because if we have the arm, then the forward kinematics will be fixed. And then we can take the differential of that to get the Jacobian matrix. This is easy for the human side, but for the swarm side, we cannot have a text, such a kind of text function. So we need to design a text function for that. So we consider that each of the robot have the dimension has the degree of freedom R. And if we have N robot in the swarm, then the total dimension will be NR. But the human is not able to interact with the dimension, the text function with the dimension NR. So we need to design a task. So the task it defined here is XR and XR door. And then which those two should have the same dimension as the master robot. So how to design that? Because this is like artificially made text function, so we can best one we want. So easily, we want to control the average, precision, and the variance, so that we design this two function for those things. In addition to that, when we design the test function, we need to make sure that the differential of the test function will generate a continuous differentiable Jacobian matrix, so that we can use the Jacobian matrix to control the swarm in the null space. So these are the two main tasks that we consider. One is the centroid of the swarm robot is like the average precision. So you can see the F sigma, they are just the average. If we consider the grounded mobile robots, we will have X and Y position, then this will just XY average position. In addition to that, we want to control the variance of the swarm robot. So we will use this to compute the variance. And then because Jacobian matrix in this research is important to ensure null space control. So we need to take the partial differentiate to get a different column for the Jacobian matrix. So these are just two basic examples, because other functions that can characterize the behavior of the swarm robot would also be considered and designed in the text function. So by doing that, we can see, okay, here, this is one example that if we fix the average precision and fix the variance, so you can see that the swarm robot might close to a certain part, still satisfying the desired average precision and the variance. But if this is not what we want, what can we do? So after the main task, the next part is to design the secondary task in the null space. So in the controller, we have a function that's called the psi-s. This is auxiliary function. So we can use this auxiliary function to control the secondary mission of the swarm robot. So how to do that? Auxiliary function is just the gradient of this can f of qs. This can be considered as a potential function. So if the functional value is smaller, then the system will more satisfy, more fit to our desire. Okay, so we can use that to define different secondary tasks. Here are two. One is that the inter-robot distance. If we don't consider that, robot might stay in this form, okay? But if we want to enlarge the region covered by the robots, then we can use inter-robot distance in the secondary task. Another one is the collision avoidance. So if we know the obstacle in the environment, then we can use this function to measure the distance from each of the swarm robots to the obstacle, and then make sure that they can avoid colliding the obstacles. Okay, so after talking about the structure, the main text and the secondary text, we have done some experiments. So in this experiment, we have a human operator manipulating a phantom OMI devices. It was phantom, but now it changed its name to geometric. And then the human will interact with 4 epochs. And then the communication delay between these two are 0.5. So in the following, the end effector of the phantom will be XYZ. So we will use this XYZ to control 3 main tasks of the swarm robot. So there are 3 different experiments. The first one is that these 3 XYZ controlling the XY average precision of the swarm robot and the variance. So you can see that the human can change its XY average precision and the variance. In the meantime, the mobile robot will avoid colliding the obstacle in the environment in the secondary task. So the human doesn't need to know that. And the second one, we change the formation. So we make the human to control X and Y variance individually. So if one of the variance is 0, then the swarm robot will keep a line in the vertical or in the horizontal. In addition to that, the third axis is utilized to control the position of the formation. The last one is cooperative transportation. We remove the secondary task for collision avoidance. And then the human can enlarge the variance and move the robot to surrounding the object and then decrease the variance. When the variance is decreasing, the robot will close to each other and then holding the object. Then the human can move the desired precision of the X and Y average precision so that the object will be transported by using human operator. So based on here, we can have the text abstraction providing the human to interact with the swarm. So the main task can be the average precision or variance. But this is not enough. Like in Professor Nepal's talk in yesterday, in the plenary talk, she mentioned that decentralized is very important for swarm robots, because if the number of agents is increased significantly, it's not possible to have a centralized. So before here, we focus on centralized, because if we want to have the average precision or the variance, we need to know what is the agent's precision. So due to that, we extend our centralized framework to a decentralized control system. So for the decentralized, basically we assume that there is only one or a part of a robot in the swarm can interact with the human operator. And then the other agents, they need to estimate several information. For example, if we want to control the X and Y average precision, then they need to estimate what is the total average precision. So here we utilize the PI estimator to get that. In addition, because only one robot in the swarm can receive the command from the human. So the other robot, they doesn't know what is the main task. So we also need to estimate the command from the human operator. So in the decentralized framework, we also done some experiment. So in this experiment, the communication delay are non-identical, and then we still consider three main scenarios: the area coverage, switch information, and cooperative transportation. They are kind of similar to the previous one, but this is in the decentralized manner. So for the average for the area coverage is the same. The human can, so these are the tracking, the main task tracking error, okay? So the blue line, the blue dot is the average precision assigned by the human, and the red dot is the average precision of all the swarm. So you can see that they will follow the command, and then they will not hit the obstacle. So in this framework, we don't need to precisely control the position of the swarm because it's text abstraction. In the second one, we consider this as switch information, but it's just we use the rotation of the formation. So you can see that if we can change the one of the tasks, then the swarm can rotate clockwise or stop running. And the last one is for cooperative transportation. So the same, you can see that we can change the variance. So now when the variance is decreasing, they will close to each other. And then the human can enlarge the invariance and then move the robot away from the object. So we don't need to control the robot individually. It's they are controlled as simultaneously under the framework. So this is for grounded mobile robot. And Professor Lee just mentioned that 2D is easy, right? So we are thinking whether it's possible to extend the results for the 3D, but we are still working on that. So in the 3D part, we want to use two geometric touch, and then the human can hold two geometric to interact with a multiple drone, okay? So we want to have more than that, but the current result we have is only for 3 crazy fly. So in this experimental result, you can see that a human is holding two geometric devices. One is to control the XYZ average precision of the drones. Another one is to control the XYZ variance. So we can see that when the human using the devices, the crazy fly will follow the command. In addition to that, we ask a human, another student, to hold a marker and walk into the workspace to see whether the drone will interact with the presence of the human. And the experiment we done here is based on the decentralized framework. So we can see that maybe this got some potential. So in the future, we want to enlarge the number of the robot in the swarm and then try to implement this system for the 3D dimension, 3D robots. Okay, so end up here, we consider the human swarm interaction, but those is based on the main task designing to represent the behavior of the swarm, like the average precision or variance. Okay, but sometimes this might not have good enough application, and we are still thinking about that. So by following that research, in the next one, we consider a different part that's called the leader-follower human-robot interaction. So in the text abstraction, we use the average precision and the variance. So the robot are considered as a 1, okay? But inside here, the robot are considered different. We have a leader, we have follower. So there's only one robot in the swarm will interact with the master robot, that's called leader, and the others are called the follower. So inside here, we want to control the any factor of the mobile manipulator to follow the command by the human. So they are different because they just like trajectory tracking. In addition to that, each of the mobile manipulator is a redundant system. So we can control its mobile base to avoid obstacle or to achieve some other constraint like velocity or joint angle. So for this part, I might not have enough time to go through, so I will just show you some results. So this is a simulation results. We have OMI to operate in a 3 mobile manipulator to control the any factor. So while the any factor tracking the command from the human, if there are some obstacle in the environment, the mobile base will change its position to avoid that. And in this research, we consider time varying delay, actuator partial loss, and the disturbance. So this is the basic what we need to do that. And this is a decentralized framework. So each of the robot, they need to estimate the state of other agents and also the main command from the human. And then we done some experiments, and this is still ongoing because we use several self-made mobile manipulator and then still use a geometric touch to control that. So in the experiment, you can see that the any factor of the mobile manipulator are controlling by using the geometric commanding by the human. Okay, so the mobile base will move along with that, and the reason because there is no obstacle. So the horizontal plane position are moving just like contributed from the mobile base. But if we add some obstacle in the environment, we can see that the any factor to follow the desired trajectory, then the mobile base, sometimes they need to change its position to avoid colliding the obstacles. Okay, so let me wrap up this research. So we have been working on the multi-agent system and teleoperation system, but to make the multi-agent system have more applications, we combine them to present the human swarm interaction. So in human swarm interaction, based on the text abstraction, we provide two approach. One is for centralized, another one is for decentralized. And then for decentralized, we want to make the system have more applications so that we also propose another approach for the leader follower framework. So in this research, we believe that they will have a lot of potential application because the first one is a scalability. We can increase the number of the robot in the swarm, and then all the swarm will be represented by only the main task. In addition to that, we can have a higher flexibility because we can change the main task, we can change the secondary task according to the applications. And then we also consider the communication delay between the swarm and the human, and also force feedback. Because if the human can feel something, which means that we will know what's going on for the swarm in the remote environment. But this also leads to our future work, because human might feel the force, but it doesn't know where the force comes from. The force might come from the difference of the main task. It also could come from the swarm robot interacting with some obstacles. Okay, so what is the meaning of the force feedback will be our future work. In addition to that, like cybersecurity or different application will also be considered in this research. Okay, so this is about my talk. Thank you very much for your time and listening. Thank you.
Thank you for an interesting talk. We are now open for the questions. So if you have any questions, please come to the microphone. Or if you have any question, please pause it, Slido.
Thank you for the interesting talk. I have a question about feedback to human. What do you feedback? All position of robots?
Sorry?
What information do you feedback
okay.
to human?
To the human.
Yes.
Let me go back. So basically, we take the position and velocity of the mobile robot in the swarm to feeding back to the human. It's not here. So inside the control system, like here. So they need to exchange position and velocity. The position and velocity of the local robot need to be sent to the central station for the swarm robot. And then the swarm robot. So if for the centralized manner, there could be a center station. So this center station will collect all the position and velocity from the swarm. Okay. And then in addition to that, this center station needs to receive the position and velocity from the human. And then the controller is implementing inside and then sending the individual command to all the swarm. So this is the centralized part. Okay. But if it's for decentralized, only the receiver, we call that receiver, can need to get the velocity and position from the human. And then the robot in the swarm, they need to exchange their position and velocity and also the estimated results, like average position and variance to their neighbors. Okay, so I don't need to send to all the other agents. I only need to send to my neighbors. So here we consider unilateral connection. It should be a balanced graph. Okay, so in that case, they will have enough information to estimate for the main test.
So in distributed control, you don't need to communicate with all robots.
Yeah, for the
Alright.
decentralized part.
They can estimate.
Yes.
Okay. One more question about the position, average position.
Mhm.
Maybe you can. Is there do you have other idea, or because I think you thinking average position, but you have velocity. So maybe you can combine position and velocity to feel.
Okay. The main reason is that if we design the main task, we need to take the differentiate to get the Jacobian matrix. So if we take the velocity inside, then when we do that, the Jacobian matrix might not be feasible to have the null space. So that's the reason we only take the position in the main task. But that's a good suggestion. We can think about that to see whether this is feasible for the whole system.
Yeah. Thank you so much.
Thank you very much.
Thank you for the discussion. And I think the time is kind of wrap up. So yes, thank you for the great speech.
Okay, thank you.
And we can move to the next speaker.